So, good morning to one and all. So, in this video, we'll try to discuss about the interdigital bandpass filter. So, how can we design interdigital bandpass filter? Uh, so that's we'll try to see. So, I have taken a IEEE paper, conference paper from the International Conference of Communication Networks. So that's is from the Rani Durgavati University, Jabalpur. The two authors, Atul Makari and P.K. Khare. So this is a five-pole interdigital bandpass filter. Actually, this is a symmetric one. So what do you mean by symmetric is the lengths of the first and the last poles are equal, and the second and the fourth one, the third one length would be different. Spacing is the same. But I don't want to go into the detailed discussions about what is a bandpass filter and how do you design the bandpass filter, like what are the what do you say specifications you need to take care for bandpass filter. I think those are the things you need to take care. And if you wanted to design any bandpass filter, the theoretical concept you have to learn it according to yourself. So, but I'll just give a brief of like why do you need to, like what are the things you need to uh, so what are the things you need to focus on, that things I'll just consider it. So you need to understand what are these. So these are the VRs, and so this is a five pole interdigital bandpass filter, and there is a theta. So let's calculate the electrical length, and this is conductance, mutual conductance. So how do you calculate the mutual conductance? Again, with the electrical length and the G parameter values. So how do you calculate the G parameter values? Then again, there is a ripple factor, and N is the fundamental concept. So N is the number of poles or number of lines you wanted to design. So fundamentally, if you want to design any bandpass filter, these are the things you need to have. What are the 3 dB frequency points and rejection points, 3 dB frequency, what is the bandwidth you want, and what is a fractional bandwidth, and what is your substrate, and what is the thickness of your substrate, and what is the stop band frequencies, at what band, at what rejection you are trying to stop these frequencies. So these are the fundamental things which you need to estimate, and first starting from there you need to calculate all the parameters, the length, width and spacing between all these things. Once you do these things, you can get this. But if you have ADS tools and AWR tools, so you can have Wizard also, like passive control window, where you can import the values, these values, and you can get the calculations. But I would say that try to do your calculations on your own, and at the end you'll try to get these values. So so I'll try to show what are the values we'll get. So at the end, you'll try to get these values. So this is the end box. So these are the important values. So today we are going to design this interdigital bandpass filter with these values: the width L1, L2, L3, L4, and so the S12, S45, and these are the spacings between them. And the VR size, I think we will have to just study what is the VR size over there, or I'll just give it as minimum as possible. And let's see what is it. Let's take 30 dB as the rejection points, and I'll try to assume 30 dB here. So there's only 25 dB. Let's check 25 dB. So that 25. This is the stop band rejection points, and this is the pass band rejection points. So this is FP1, FP2, FS1, FS2. So this is around 1.524 gigahertz. So and this is up to 3.2, and this is up to around, let's say, 1.7 or 1.8. So that's a quite point. So the fractional bandwidth is around 60%. So it's a quite wideband bandpass filter. So it's not that difficult if you have a wideband bandpass filter. It is easy. So ensure that you have to have the proper return loss. At one point you have this peak. So let's see how we can design. So let's not waste the time on more technical concept. Like we'll directly jump into the ADS design software, and we'll directly go to the layout window and start designing from there. So I'll try to open a new workspace. If you are very new to the ADS software, so I think I'll explain in another video, or like how can you get into the ADS software, the basic demos and everything. So I'll try to open a new workspace. I'll create this as Interdigital BBF video. I'm creating for the video purpose, so that's why I kept as a video. So you have to choose what is the topology, like what is the millimeter layout resolution you want. Standard ASA, I'll go for the 0.001 millimeter. I'll mostly finish in the millimeter range. So now I'm creating a layout. So directly I'll jump into the layout design rather than the schematics, layout and symbol. This is a schematic window, this is a layout window, and this is a symbol window. So I'll try to create the layout. Interdigital. So now we have appeared the layout. So let's see the let's see. This is the interdigital filter. So now we have this. First, we have to see that this one. So this is a table length. So now I'll try to design from here so that you could also understand. So first length is this one. First, this is this one. So we have this length and width. So the width is always mostly constant from here to here. So this length and this length would be similar. So this is the taper length, and we'll see what is the taper length. That is LT, that is 9.6 mm. Did they give the tapered width? No, I think they did not give the tapered width. But I'll assume the tapered width is as similar as the all the width. So that is 4.55 mm and 9.66 mm. So we'll go to the design window and we'll take a so generally it's now this is when we wanted to draw a trace. So either you can use a rectangle or you can use a trace, whichever is possible. So I'll use a rectangle one. So this I've drawn a rectangle. Now once you click on the rectangle, you can see the height and width. That means you have the length and say. So now the it is 4.9 mm. Don't need to write the mm because already we have taken as mm. And height is a substrate, so that I will take it as so what is that? 9 length is 9.6 and width is 4.55. So length is 9.6 and width is 4.5. So if you want to just see all it, you can just scroll up and down. You can have this. So this is the best one which I got. So this is to take all the four points if you want to connect to the points or if you want to measure it anything. Now, if I wanted to move this, there's this symbol called move with a reference point. And you go there and you can just move that point. So now I have done this one. So now next is I have to see where is the next one. So I have to design this stub. Okay, resonator stub. This resonator stub. So I have to see this resonator stub with the first length, which is around let's say this is L1 and W1. So let's see what is L1 and W1. So L1 and L5 are 16.005 and W1 is 4.55. So let's see what is L1. So I'll try to draw like this. So I'm not connecting right now. Afterwards, I'll draw connector with 16.005 and 4.55. So this is that. I'll make sure that it is near. And this is the 16.005 and 4.55. And next is what is the stub of L2 14.50545, and what is it? W2 is 4.55. 4.55. So 14.55 and 4.55. Now I have to go it again here. So I'll take here one more rectangle. Draw this. So currently I'm not giving the spacing right now. So there's one more stub only. So I'll just finish off these lengths and everything. 14.545 and your width is same 4.55. So I think I got this correct. So 14.545 and 4.55. So that's there. And we got the second, and we have to have the third one. So again, the third one would be quite bigger compared to the second one. L3, L3 is again 14.54 and 4.55. So L2, L3, L4, and are same. So now instead of drawing it again, we can just click on this one, and once you can say the symbol, so this is copy with reference point. Just you click on it, and you click on any reference point and just drag and drop. So it's a very easy and very easy one in the ADS layout window. So now you have L1, L2, L3, and L4 is also same. So again I use this copy reference point and I change this one, and I need L5, that means L5 is this one. So I use this and I keep it over here, and I need again the tapering one, so this is again there. So I use this. So now we have created all these things. Now the main point is to give the spacing. So the spacing between one step to the another step. So one method I use varies. I try to change this everything is in con layer. I just try to change it into any other layer. Generally I go for the whole layer. Generally I go for any whole layer. So this is way method. So I try to use the whole layer. So now what is it? I try to see what is S12, S12. So S12, that means the spacing between the first and the second stub. So the spacing between this one, the first and the second stub is what is the spacing they're given? So that is 0.22 mm. So I'll try to create a rectangle of 0. What is it? 0. 0.22, and I'll see 0.22 and 0.22. Oh, spacing is so little, so I'll just have this one. So I use the move option over here. So once select this box, and so you can keep it at center, and for this one you can go to this center and you can click on this. Now you can take again the move option, and you can have this move center and again go inside center. So now you have the spacing between those 0.22 to 0.22. So that's there again. Now what is the spacing between the uh, L2, L23, that is 0.32 mm. So now again I have to go to this 0.32. So Now I'll try to create a 0.32 and 0.32. I'll again move this one, keep it in the center, connect it 0.32. So I've done this one. So now there's always copy paste only. So we have done this. So L1 is done, L2 is done, L3. So L3 to L4, that's again 0.32 only. So just copy this one and move this one to here. And again for the last one, that is 0.22, I'll just try to move this, copy this one. So over here, I just copied that, and you can see I'll try to move this one to here. Okay, now we have all the planes. Now I'll try to delete all this and um, so we have created the five stubs L1, L2, L3, L4, L5. So now we have used the whole layer and gave the space between them. Now we have to uh, attach these stubs, I mean the tangent stubs. So what I'll try to do is I'll try to move this center and try to connect in the center. So it doesn't matter where are we trying to connect. And now we can remove this uh, holes. So how can we remove? So just click on it and delete this. Just click on it and delete all these things. Once you delete, you have this all. Uh, so we have removed that, and now we have the spacing between those layers. So the only thing left in this is the entire structure is we have created everything, just we have to create that vias. So what is the via size we have to see, and where did they mention the via size? Did they mention anyway the via size? Generally the via size is around uh, the thickness of the copper conductor. This is create a HFSS, we have taken 1.6 mm. SR4 substrate 1.6 mm they have taken. So resonators we used. So the radius of the via is zero point 0.4. Zero point 0.4 is the via radius. So they have over here zero point 0.4 is the radius. Yes. So now we go to this layer. Now first, so there's a bound. There's a layer called bound. So I'll show you how we can create that bound. So before that, just try to take a circle. Go to this whole layer. Try to take this circle, and if you click on the center one, this one, the point, the radius is, you can do this here afterwards. I'll tell you. So once you have created this, you have to see the radius is 0.4, 0.7, and what is the radius is then zero point 0.4. So zero point 0.4 is the radius. So I'll change it to 0.4. So that's it. Now how can we make it very simpler? Just copy this center, go to zoom, little zoom, give one more here. Okay, now you have over 3 over there, and I have to copy this and put it in the over that side. So I'm not exactly placing in them in the between. I think there would be a slight difference on that, but we can do that also. Just you can take this and try take a line from here and take a line from here and see the depth, how much inside you have to keep. So that's again a parametric optimization. So now the main thing from this point is we have to create that EM simulation setups. So click on this EM part here, create new EM setup, and once you have done that, you have to change whether you want to go for MOM method or FEM. So I'll pick FEM. So so we have to create a substrate. So I'll name the substrate as FR4. Mhm. So now we have this substrate. Now what is the thickness of the substrate? We have to see. So I think that's 1.6 mm. Uh, 1.6 mm FR4. So 1.6 mm we can write that in mm also. So 1.6 1.6 mm, and now we have to change it into the FR4 substrate. So how can we change that into FR4? So there's a three dots over here. I click on those, edit materials, click on the data, add from database, and you can see FR4 is also there, 4.6 FR4 croak big bag, and so you can click on this 4.61. So okay, and apply. Now you have to change this one to FR4. So you have this FR4. So just click on this cond and click on this imbued. So thickness is 35 micron, which they have mentioned over there. And now there's one more thing. You can change this cond layer. This would be the ground layer actually. So this I have changed it to 35 micron. So either you can make it as perfect conductor or you can take that as again a conductor. It's up to your level. So copper. So we can change this again into the copper. So that's up to your level. So even if it's a perfect conductor, it won't matter that much. So now I've done this. Now the main important is insert the conductor via. So right click from this one, right click, and you'll have a insert map conductor via. So click on the conductor via. You have this conductor via, and already. Why did I use that whole layer? Because automatically in the ADS, once you insert a conductor via, there the hole comes under. So once you insert a conductor via, that's there. That's it. Now you can save and close this one. And the only thing which is remaining is the ports. We have to assign the ports. And I forgot to mention how can we import the bound layer. So map bound layer. So bound. Where does the bound come? Layer map conductive. Okay. Okay. Now you can see I've clicked on this add new layer and you have bound. So I've just clicked on bound. So what does the bound do is like you have a finite restrictions on the substrate body. So I've changed that. So now you can see there is a bound layer. See bound. Previously it did not appear. Now you have appear. So take a rectangle, give it a go. Okay. And either way you can keep it as minimum as possible, or you can. I'll try to put in this method. So I'll try to see this again, what is the distance from here to there also. So if you want to see the distance, press Ctrl M, that is measure, So that's around 2.8. So we'll make it as 3, approximately 3. So 2.8 is 1.2 approximately. So now again I'll see from here. So it's 5, so minus 2. I'll try to minus 2. So I think it would be around 3 now. So that's 3.6. 3.4. I'll just decrease zero point 0.4 from here. 0.5. Okay. I'm not making it as exact as possible, but I'm trying to make it different. So there's one more thing, you need not to import a ground layer, or because already it's there. Already the con layer is there. That's a copper one. So you can always intrude, like add one more layer. So that's there. Okay. For now, time being, we'll stop this because of the time constraint. Now I'll directly add ports. So when you have insert pin, you take this pin, put it over one pin, put it over one more pin. Okay. You have 2 ports. So you have this. So now the substrate has been formed. So now you have to see what is the frequency plot they have done. So I have to see the plot. So 1 to 4 gigahertz they have plot. So now I'll try to do that. Frequency plan 1 gigahertz to 4 gigahertz, and so that's it. Click on simulate. You will start simulation, and once the simulation is done, I'll show you. So the frequency plot has come like this. Generally they direct pop up the window. So instead of that, you can take there's one more here. You can take this box, the rectangular box, zoom it, and you can have this ports. You'll have this port S11 and control S12, S21, S22. Add DV and OK. Now you have this plot. So 1 to 4 gigahertz. So we have around 10 dB. So I'll take a marker, new line. So the spot on frequency came around 2.2 gigahertz. Okay, for me it came around 2.2. So, and we'll take one more new marker. So one here, M2, so M4, and NC. So it's 122 dB. I will see that. So 1.3. 4 gigahertz. At 4 gigahertz around 22 dB, and I'll see whether at 4 gigahertz it's around 25 dB. So similar point of view. At 1 gigahertz around 40 dB it has. So let's see at 1 gigahertz. So at 1 gigahertz it's around 40 dB. So the results came quite good. So there's not much difference in the results. So based on the placements of the vias, if you want to change the frequencies, you can change the length, radiating slot lengths of the vias. And if you want to 3D it in the 3D, you can just type the 3 and okay, and you can see that in the 3. See, now you have this slot. So there's a con layer. That's it. So these are the slots and these are the vias. Actually, ground layer, there's a ground layer because of the substrate we have kept here. There's a medium plane as ground. Next time I'll show you how to insert a ground lane from there. So this is a concept of how to do the band pass filter design in HFSS ADS rather than HFSS. So it's quite simpler than the HFSS software. So it takes very easy, and the only thing it is a little difficult in the HFSS ADS over than HFSS of the parametric optimization. We don't have easy method for doing the parametric optimization. But if you have the correct values and calculations, it's easier to do, and you can do it in 15-20 minutes. So that's it, guys. Thank you for the video. Thank you for watching it. And if you want more videos, you can sign in into my LinkedIn account. It's Nagraj. Thank you. I'll drop a link to my LinkedIn profile in the description. I will look through it. Thank you.